Welcome to lecture series on advanced linear algebra. We have studied in physics, even in 11, 12 and well in mathematics also, a vector quantity over the space R3 as a quantity having magnitude as well as directions. I mean to say, if you consider say alpha, which is equal to x1 I plus x2 j plus x3 k, and beta equal to suppose y1 I plus y2 j plus y3 k, then we have seen that scalar product of the two vectors alpha dot beta, that is basically over the real lines, it is x1 y1 plus x2 y2 plus x3 y3. So, this basically it is saying that of alpha into length of beta into cosine of angle between alpha and beta. So, that is what we have learned in our in 11, 12 for the case of the dot product of two vectors, where we see that vector quantity having magnitude as well as angle. Whether similar concept can be introduced over our generalized vector space or not. Similar concept can be also introduced over the vector space by introducing the concept of inner product. What is inner product, please? Inner product. Before talking about the inner product, here also we have to say, though we will basically restrict to our angle as perpendicular of these two vectors or orthogonality of the two vector space. So, let me define what is inner product on a vector space. Let V be a vector space defined over set of real numbers or set of complex numbers. I mean to say, the field is basically either real number or complex number. An inner product in V is a function which assign to each order pair of vectors to a scalar quantity in the name of like this inner product, please, such that first for alpha, beta, gamma belongs to V and C belongs to capital F. I mean, F is basically a field over which the vector space is defined. We have to consider F may be real number or may be complex number. So, it satisfied first alpha plus beta, inner product of alpha plus beta comma gamma equal to inner product of alpha gamma plus inner product of beta gamma. This is called linear property of the inner product. Second, inner product of C times alpha and beta equal to C times inner product of alpha beta. Third, inner product of beta alpha equal to complex conjugate of inner product of alpha beta. Inner product of beta alpha is equal to complex conjugate of inner product of alpha beta please. Fourth one, inner product of alpha alpha is strictly greater than 0 for alpha not equal to 0. And based on the axiom 1, 2, 3, we can also write another axioms is like that, inner product of alpha C times beta plus gamma equal to C bar inner product of alpha beta plus inner product of alpha gamma. So, here we have seen definition of the inner product like this. Say suppose a function, it is a function from V cross V to the field F, which is mapping any alpha beta order pair to a scalar quantity like this. Okay. So, this is the basically inner product I am defining here. So, based on this you can see one thing that if you do not consider third axioms, that is inner product of beta alpha equal to inner product of alpha beta bar, then this fourth axiom will not remain valid when you consider the vector space over the complex number. For examples, inner product of say I alpha and I alpha. If I write simply this is equal to I square inner product of alpha alpha, where alpha is a vector, I is a imaginary quantity. So, this I am getting is equal to minus inner product of alpha alpha, which cannot be greater than 0. So, therefore, to satisfy the fourth axioms we need the third axiom please. So, now let me consider some examples. So, let us consider a very trivial example in the sense of our usual space, that is space of n tuples. Let V equal to space of n tuple over the F. Consider psi from V cross V to F for alpha equal to, let me consider n tuple x1, x2, x3 and xn, and beta equal to y1 to yn. Let me define the inner product psi alpha beta, which is equal to inner product of alpha beta. I am denoting, suppose is like this, xj and yj bar, j equal to 1 to n. If I define a function like this, psi of alpha beta equal to sigma xj yj bar, then claim this function basically introduce an inner product over the space V equal to Fn. So, to prove that once I have to prove that it satisfied all these first three axioms as well as fourth one also, because fifth one is coming as a consequence of first three. So, I do not want to do for fifth one. So, 1, 2, 3 and fourth one. So, first the linear property. See, we have for alpha, beta and gamma belongs to say Fn, gamma equal to say Z1, Z2 and Zn. Okay. Now, if I consider psi of alpha plus beta comma gamma, according to this one is equal to inner product of alpha plus beta, according to this definition sigma xj plus yj into zj bar over the j. So, j equal to 1 to n. So, this is equal to sigma of xj zj bar plus sigma yj zj bar. So, this implies psi of alpha plus beta comma gamma, which is equal to inner product of alpha plus beta gamma, which is equal to, we have this is inner product of alpha and gamma plus inner product of beta and gamma. So, linear property holds good. Second one also you can see it easily, and psi of C alpha comma beta, if we consider like that, this is equal to sigma C xj into yj var over the j, which is equal to again C, you can take it out over the j equal to 1 to n, you will have xj yj var, which is equal to C into inner product of alpha beta. So, second is also holds good. Now, third one, psi of beta alpha, psi of beta alpha equal to yj xj bar, j equal to 1 to n, again psi of alpha beta, this bar equal to sigma xj yj bar whole bar, and this is equal to sigma, I can write on yj bar bar, that is yj and xj bar, j equal to 1 to n. So, if I consider this is 1, this is 2. So, 1 and 2 implies that psi of beta alpha equal to psi of alpha beta, that is inner product of beta alpha bar. So, inner product of beta alpha is equal to inner product of alpha beta bar please. And the fourth one, psi of alpha alpha if I consider, that is equal to sigma xj and xj bar. So, this is equal to sigma mod of xj whole square over the j. So, for alpha not equal to 0, definitely there will be some xj not equal to 0. So, we will have sigma mod of xj bar is strictly greater than 0. So, it introduces an inner product over the space Fn. This inner product is called the standard inner product. So, this inner product on Fn is called as standard inner product on Fn. Let me take another examples. So, let me consider space as set of all n cross n matrix. Let V equal to F n cross n, that is set of all n cross n matrix over the field capital F. Let me define a functions psi from V cross V to F as psi of AB equal to sigma Aij and Bij bar. So, the index is over both I and j please. I mean to say it is sigma I, okay, this is all equal to 1 to n please. I mean to say sigma I equal to 1 to n, sigma j equal to 1 to n, aij and bij bar. So, we can quickly show that this function psi also introduce a inner product over the space V. See, we have psi of a comma a for non-zero matrix A, we have this is equal to sigma sigma your mod of aij whole square, which is strictly greater than 0 for a not equal to 0. So, this implies inner product of a and a is strictly greater than 0. Okay. So, I am defining inner product as a function psi of a and a comma a, which is equal to inner product a comma a, I am defining as sigma I equal to 1 to n and sigma j equal to 1 to n. Here I am getting as a mod of aij whole square, which is positive quantity. So, it satisfied that fourth conditions, and we can see linear property also holds good. For linear property, we have psi of say a plus b comma c, a plus b comma c, that matrix is equal to sigma sigma a plus b ij and c ij bar. So, this is equal to sigma sigma a ij c ij bar plus sigma sigma b ij and c ij bar. So, we see that, so this implies psi of a c and plus psi of b c, that is inner product of a c plus inner product of b c. So, inner product of a plus b comma c equal to inner product of a comma c plus inner product of b comma c, please. So, linear property also holds good, and you can also check c into a comma b equal to c times inner product of a comma b, that we can prove it easily from the definition itself, please. So, it also give an inner product, please, over the same over the space, please. Now, over the same space, let me consider another function over the same let me consider another function say phi from V cross V to F, defining by phi of a comma b equal to a b star I I. Okay. So, this is over the I. So, this means that trace of a b star basically. So, if I define a function phi from V cross V to capital F, please, at phi of a b equal to summation of a b star I means sum of diagonal elements of the product a b star, then this will be also give me a inner product, please. Okay, so, we see that this is equal to basically sigma over I, and you know this is equal to again sigma a I k and b star k I. Okay. So, this is over k equal to also 1 to n. So, this is equal to sigma over I as well as k, this is a I k and b star means conjugate transpose. So, this means that this is equal to B I K and bar. So, this implies that phi of A comma A will be also positive definite quantity if A not equal to 0, and you will also see that it satisfies linear property, it also satisfied that constant second axioms, and it also satisfied the third axiom that phi of A B equal to phi of B A bar, bar of phi of B A, please. One you can check phi of A B equal to phi of B A bar. So, as I did for the first example over the same space, this same thing can be do for this, can be used for this function also, and here also you can show that this phi introduces an inner product on your space as a f n cross n. Okay, so we have taken space as n tuple space, space of all n cross n matrix, and we define some inner product. Now, let me take some more example on different spaces, please. So, this will be example number say 3. Okay. So, here let V be the space of all continuous functions in a closed interval A B. So, it may be real valued or complex valued depending on the field, please. So, let me consider in general as a complex valued function, please. So, now I will introduce the inner product as like these notations, which is basically functions which is mapping from V cross V to F. So, I am writing now for sake of simplicity like this, that for any element F and G, F inner product F comma G, this is equal to, I am defining as inner integration of 0 to 1 f of x and g of x bar dx. So, this is an interesting example in our mathematics, specifically in analysis, which will be used in different cases. So, this function, if I consider that say psi of f of f comma g is equal to like this, psi is a function from V cross V to capital F, then this function psi is an inner product. I have to again to check whether it is inner product or not, I have to check all the 4 axioms. Linear axioms, we have inner product of f plus h comma g equal to inner product of 0, integration 0 to 1 a plus g of x a plus h into g x bar dx. Since integral is a linear operator, so in that way I can write down this is equal to 0 to 1 f x g x bar dx plus 0 to 1 h x g x bar dx. So, this is equal to inner product of f and g plus inner product of h and g. So, linear property holds good. Similarly, second property also holds good, we can check it, and let me check the third ones. Third one is also very trivial, inner product of f g equal to, if I take the inner product f g bar which is equal to integral of 0 to 1 f of x and g of x bar dx, this whole bar, and this is equal to 0 to 1 f x bar and g x bar bar, which is equal to 0 to 1 f x, which is equal to inner product of g alpha g f. So, inner product of f g bar is equal to inner product of g f. So, third one also holds good, and fourth one inner product of f f, which is equal to 0 to 1 f and f bar dx, which is equal to 0 to 1 mod of f square dx. Since this is a positive definite functions and you are integrating over the integral 0 to 1, certainly it will be greater than 0 for f not equal to 0. So, it satisfied all the axioms of the definition of inner product, please. Now, let me introduce another examples which is very much interesting one. So, let V and W be two vector spaces over the field say capital F. Now, let this be an inner product in W, but nothing is given about the V. Now, let me define a functions consider function Pt from V cross V to F as follows. Let T be a linear transformations from V into W and T is 1 1, I mean that is non singular. Now, let me define Pt of alpha beta for alpha beta belongs to capital V. Define Pt alpha beta equal to inner product of T alpha and T beta. I am defining a functions Pt from V cross V to F, which is defining for which is mapping any order pair vector of V to a scalar quantity inner product T alpha T beta, which belongs to F, please, because since this inner product is given in W, so I can define it like this. So, we can check, we see for alpha not equal to 0, Pt alpha alpha is equal to inner product of T alpha and T alpha, okay, which is strictly greater than 0 because T is non singular. So, T of alpha cannot be 0 if alpha not equal to 0. So, therefore, this is non-zero. You can also check that it satisfied all the other axiom, because this is definition itself is saying an inner product in some W, but it is basically introducing an inner product in V. So, PT is an inner product in capital V. So, it introduces an inner product in capital V. So, from a given inner product in W, we are able to introduce an inner product in V, please. Okay. So, if I consider, let V be a finite dimensional vector space and B equal to alpha 1, alpha 2, alpha n be an order basis for this is an order basis for V. Let W equal to n tuple space Fn, so that one can have 1 onto map between the V and W. So, let T be a map linear transformations from V to W. Also let me consider, okay, so let me consider that T of alpha I equal to Ei. I am defining like this, T of alpha I equal to Ei, where B prime equal to E1, E2, En, the standard order basis for Fn. I have chosen the standard order basis in W. So, my W is equal to Fn base. Now, I am defining a linear transformation T from V to W, T of alpha I equal to Ei. So, certainly, so T is non-singular, T is non-singular. Let alpha and beta be any two elements in V. Since I have taken B equal to alpha 1, alpha 2, alpha n as a basis, so there is a scalar x1, x2, xn such that alpha equal to sigma xi alpha I, and similarly beta also, for beta there exists n scalar, say yi, yj and alpha j, j equal to 1 to n, here I also equal to 1 to n. Now, if I consider psi of alpha beta, according to my definition, this will be equal to inner product of T alpha and T beta. So, this is equal to, if I consider the inner product in Fn as a standard inner product, what I have considered in the beginnings, then T alpha and T beta. So, T alpha is equal to what? Inner product of, okay, T alpha is equal to T of operating alpha equal to this one. So, T of sigma xi alpha I and T of sigma yj alpha j. Okay. So, I have like this. So, this is equal to sigma xi into alpha I equal to 1 to n and sigma yj alpha j, j equal to 1 to n, this quantity. So, this is equal to sigma xi and yj bar and inner product of, so there will be another summation inner, okay, we will have T of alpha I, T of alpha j please. So, T of alpha I means Ei and Ej. So, it is basically inner product of in Ei Ej. I know inner product of Ei and Ej, if I with respect to standard inner product, it is equal to 1 when I equal to j, otherwise 0. So, this is equal to simply over the I xi and yi please bar. So, I am getting inner product giving as a summation of xi and yi bar. Here x1 to xn transpose is the coordinate of alpha with respect to order basis B, and y1 to yn transpose is basically coordinate matrix of this one. So, we are getting an inner product from the information that an inner product is defined over the W equal to Fn. From that I am also able to introduce an inner product over space V, please. So, this is the definitions and some examples of the inner product. We will talk more about this inner product in our in next lectures, but before completing this today's lecture, let me define one things. See, we know for any complex number z which is equal to x plus iy. So, this implies that z equal to real part of z and plus I time imaginary part of z, please. So, similarly, for any inner product alpha beta, if I consider over the complex field, this will be also equal to real part of inner product alpha beta plus I times imaginary part of inner product alpha beta, please. But see, imaginary part of the z is equal to nothing, one can write this is real part of minus iz also, because minus iz means, see, we are basically looking over the imaginary part of z means y. So, y can be written as real part of minus iz. So, this implies inner product of alpha beta, which is a complex quantity, this can be written as real part of inner product of alpha beta plus I times real part of minus I times inner product of alpha beta, which is equal to this plus real I times real part of alpha and I beta, because from the property of the inner product of alpha comma I beta is equal to minus I times inner product of alpha beta. So, this is a nice algebraic characteristic of the inner complex number. So, this I will use for to understand inner product more details, which we will discuss in the next class, please. So, we see that any complex quantity can be written as real part of that plus I times imaginary part of that one. So, based on this principle, for any complex valued inner product alpha beta, that can be written as a real part of alpha beta plus I times imaginary part of the inner product of alpha beta, but imaginary of alpha beta inner product of alpha beta can be written as again real part of inner product of alpha and I beta. So, these relations will utilize to understand more about the inner product, please, which we will discuss in next class.